Hello friends, I welcome you in lecture number 13 on higher order partial differential equations. From last several lectures, we are discussing shortcut methods for finding particular integral of non-homogeneous linear partial differential equations with constant coefficients. And as we know, these methods are applicable for right-hand sides, particular right-hand sides in the given non-homogeneous equation. And in last lecture we have seen how to find out particular integral when each term of right hand side, which we denote by f of xy, is of the form x to the power m times y to the power n. In short, we are discussing the shortcut method when right hand side is a polynomial function in two variables x and y. We have seen how to find out particular integral in this case, and we know that we will consider expansion of this FD dash either in powers of d or d dash using binomial theorem, and for that we have discussed one example in earlier lecture. Today also we are going to discuss two more problems when right hand side is a polynomial function in two variables x and y. First differential equation is del square z by del x square minus 6 times del square z del x del y plus 9 times del square z del y square equal to 12y square plus 36xy. Now here also right hand side function is a polynomial in x and y, and as we know, to solve this non-homogeneous equation, first we will consider right hand side equal to 0, that is we will consider the corresponding homogeneous equation, and solution of that homogeneous equation will be called as complementary function of given equation, and then we will find out particular integral. And we can rewrite this left hand side in the notations of capital D and D dash. We know that D stands for partial derivative with respect to x and d dash stands for partial derivative with respect to y. So this I can rewrite as d square minus 6 d d dash plus 9 times this is d dash square and z equal to 12x square plus 36xy. So first I have written this left hand side in another form where capital D stands for del by del x, d dash stands for del by del y. After that we are writing the corresponding homogeneous equation, that is we equate this left hand side to 0. So this is the corresponding homogeneous equation, and to solve this first we observe that this function, which is denoted by capital F of d and d dash, here f d d dash is a homogeneous function in d and d dash. We can see that degree of each term is 2 in this function. So if this f d d dash is homogeneous, then we write down the auxiliary equation, and for that we replace d by m and d dash by 1 in f d d dash and equate it to 0. So auxiliary equation will be m square minus 6m plus 9 equal to 0, and this is nothing but square of m minus 3. Therefore I obtain repeated values of m, or solution of auxiliary equation is 3, 3, that is we have repeated roots, and we know that the solution corresponding to value of m is arbitrary function of y plus mx. Here m is 3, so we will have arbitrary function of y plus 3x, and here I have two roots, so I will write down two arbitrary functions, but m is repeated, so here I have arbitrary function of y plus 3x. Here also I have arbitrary function of y plus 3x. So to make this these two functions independent, I will multiply by power of x. One function is to be multiplied by power of x. So this is going to be complementary function of given non-homogeneous equation. Now for particular integral, we will operate this this d square minus 6d d dash plus 9d dash square, that I will transfer on right hand side. So that is 1 divided by this and operated on the right hand side. So now particular integral is 1 over this f d d dash operated on the right hand side. Now here we can observe that this is nothing but square of d minus 3 d dash. If I take square of this, then I will have d square minus 2 into 3 into d d dash, that is minus 6 d dash, plus square of 3 d dash, which is 9 d dash square. So I can rewrite this as square of d minus 3 d dash, that is operated on 12x square plus 36xy. Now this quantity I can rewrite as d minus 3 d dash power is minus 2, and I want to apply binomial theorem for this, but binomial theorem is for 1 plus something to the power alpha. So I have to convert this d minus 3 d dash, this I have to write as 1 plus something. So for that, either I can take d common or 3 d dash common. Suppose I take d common, then this I can rewrite as d times 1 minus 3 d dash divided by 2 to the power minus 2. That is going to be d to the power minus 2, and this 1 minus 3 d dash over d to the power minus 2, and this d to the power minus 2 can be rewritten as 1 over d square. So in the next step we have written in this form 1 over d square. First I have taken this d common here, so I have 1 minus 3 d dash by d into d, and power is 2, so I have written square of both the quantities, and this I can rewrite as 1 plus negative of 3 d dash over d power is minus 2, because this is in the denominator. So if we write in the numerator, we have to write minus 2 power. Now this is in this form 1 plus x to the power alpha, so that we can use binomial expansion. This I can rewrite as 1 plus alpha x plus alpha alpha minus 2 factorial x square, and so on. So here we can compare this 1 plus this with 1 plus x to the power alpha. So you can see alpha is minus 2, and instead of x I have minus 3 d dash divided by d. This is going to be x in this formula, and here in the numerator I have partial derivative with respect to y, because I am having d dash in the numerator, and I have to write these terms here. So I have to check that up to which term I will get non-zero terms. For that we can observe that because we have partial derivative with respect to y in the numerator, I will differentiate this first with respect to y, and now x is considered as constant while we are differentiating with respect to y. So first derivative with respect to y is going to be 0 plus 36x, derivative of y is 1. Now this is going to be 36x, first derivative with respect to y. Now in the next step we will have to write x square, that is square of this, that is going to be 9 d dash square over d square. So now again I have to differentiate this with respect to y, but there is no y here, so it becomes constant and its derivative is 0. So I need to write only two terms, because from third term I will obtain 0, derivative becomes 0 from second order derivative. Therefore I have written only two terms in the binomial expansion also. Before writing the series we can decide in this way that up to which order we obtain non-zero derivatives. So we have to write, or we should write only those terms for which we obtain non-zero values. We can write one more term here if we wish, but that is making 0 contribution, so I have not written. Otherwise, in the next step, I can write minus 2 into minus 2 minus 1 over 2 factorial into square of minus 3 d dash over d. And this I have rewritten again, and here also we can see that 12 can be taken common, and because it is constant, I have taken 12 common from these two terms, and I have written it here 12 over d square, and this negative negative positive 2 into 3, that is 6 d dash over d, and that we have to operate on x square plus 3xy. Now first I apply this term, so 1 into x square plus 3xy, that is x square plus 3xy as it is, plus 6 by d into derivative of x square plus 3xy with respect to y, that is going to be 3x. So that I have written here 6 by d as it is, derivative of this quantity with respect to y, so x square is constant, its derivative is 0. Here 3x is constant and derivative of y is 1. Now here d stands for derivative with respect to x, so that 1 over d will be integral with respect to x. In the next step, I have to integrate this 3x with respect to x. And here I have written 6 into 3 into integral of x with respect to x. That is going to be x square by 2, and 2 will get cancelled with this 18, that is 9x square. And this again we can rewrite as 10x square plus 3xy. And here also I am having 1 over d square, that means I have to integrate this 1 by 1 with respect to x 2 times. So first integral with respect to x is 10x cube over 3, and here also we will consider y is constant, 3y is constant, integral of x is x square by 2. Again I have to integrate with respect to x, so 12 as it is, 10 by 3, and integral of x cube is x raised to 4 by 4, so 3 into 4 is 12. Here also 3y by 2 as it is, integral of x square is x cube by 3, so this 3 will get cancelled. And now in the next step we multiply this by 12, so here 12 will get cancelled, and here I have 12 by 2, that is 6. So this is the particular integral. And finally we should write general solution by adding complementary function and particular integral, and these phi 1 and phi 2 are arbitrary functions. So what is new thing in this problem is, here it is possible to write down f d dash as square of d minus 3 d dash, that is square of linear factor. The same problem can be done by considering either d square common or 9 d dash square common, but you can see if we write in this way, then it will be comfortable or easy, steps will be easy. Otherwise we can rewrite this as we can take d square common, and 1 minus 6 d dash by d plus 9 d dash square by d square, and here also I can write this as 1 plus something, so that 1 plus something is going to consider two terms here, and here you can see we have 1 minus only one term, 3 d dash by d. So whenever you are applying binomial theorem, and if your function is homogeneous, if f d dash is homogeneous, you should check whether it is possible to write it as a square of linear factor like this, and then you can apply binomial theorem in this form. I have taken another example also. This is another non-homogeneous equation in which right hand side is a polynomial in x and y. First I have written in the notations of d and d dash, this is d square plus 3 d dash plus 2 times d dash square z equal to x plus y. The corresponding homogeneous equation is write 0 instead of this, and you will have this. Here also we can see that in this function of d and d dash, each term is of second degree, therefore this is homogeneous. And the auxiliary equation is written by replacing d by m and d dash by 1. So m square plus 3m plus 2 equal to 0. That I have written here. Now I can factorize this. I can rewrite 3m as 2m plus m. Then I take m common from these two terms, that is m times m plus 2. Here I take 1 common. And then I take m plus 2 common and m plus 1 equal to 0. That is, I have two roots of auxiliary equation, both are real and distinct. And corresponding to each value, we write complementary function. Part of complementary function is in this form, arbitrary function of y plus mx. So for phi 1 we put m equal to minus 2. For another function, say phi 2, we take m equal to minus 1. That is, complementary function is arbitrary function, say phi 1 of y minus 2x plus another arbitrary function, say phi 2 of y minus x. Now particular integral is we have to operate this on x plus y. That is, particular integral is 1 over this bracket operated on x plus y. Now you can see here this is also homogeneous in d and d dash, but it is not possible to write it as a square of linear factor. So here I have to take either d square common or 2d dash square common, because I want to apply binomial theorem. So I must have 1 plus something to the power, some power, say alpha. So for that, to apply binomial theorem, either I have to take d square common or 2d dash square common. If I take d square common, I have to divide another two terms or each term by d square. 3d d dash divided by d square, that is 1d will get cancelled, plus 2d dash square divided by d square. Now this you can compare, this is for this term, this we can rewrite in this way. Now we will consider 1 over d square as a separate quantity and we will apply binomial theorem for this. So we can operate the binomial series 1 over 1 plus x with x equal to this quantity. So that I have written here. 1 over d square, 1 plus 3d dash over d, 2d dash square over d square. I have rewritten this quantity as 1 plus something, and then I apply this series. 1 over 1 plus x is 1 minus x plus x square. Alternately positive and negative, power of x is increasing. Here also I have to write x equal to this quantity, and I have to decide that up to which power I will have non-zero contribution. Here also we can see that first numerator contains d dash, that is we have to differentiate with respect to y. So suppose I am differentiating with respect to y, then derivative is going to be 1. So derivative of x plus y with respect to y partially is 1. Now in the next step I have to take square of this quantity. So you can imagine square of this quantity is going to be 9 d dash square over d square plus 2 into 3 into 2, that is 12, and d dash to the power 3 divided by d to the power 3 plus square of 2d dash square, that is going to be 9 square of 2d dash square, that is going to be 4d dash to the power 4 divided by d to the power 4. So in each term I have more than one power of d dash. Here I have d dash square, here d dash cube and d dash 4. And here we can see that if we operate d dash on this, we obtain 1. So d dash square operated on this will make it 0. Same thing for d dash cube and d dash to the power 4. So we will write terms of this series up to single power. We will write 1 minus this quantity only, because from this quantity onwards derivatives becomes 0. So I have written 1 over 1 plus this equal to 1 minus this x plus x square will not give any non-zero contribution, therefore I have written only one term. And again I have simplified this. I take negative sign inside the bracket and write in this form. Now operate term by term on x plus y. 1 into x plus y, that is x plus y, minus 3 over d dash of x plus y, that is partial derivative of x plus y with respect to y is 1. So that I have written here, minus 3 by d dash of this is 1. And here you can see in the next step I have 2 by d square d dash square of x plus y. So d dash of x plus y is 1 and I have to operate d dash 2 times. So that is making this 0, because second order partial derivative of x plus y with respect to y is 0. So this term also will not give any non-zero contribution, because d dash square of x plus y equal to d dash of x plus y. If we operate d dash 1 times, I will obtain 1, and d dash operated on 1 is 0. So we have only this portion. Now capital D stands for derivative with respect to x. So 1 over d stands for integral with respect to x. So in the next step I have taken integral of 1 with respect to x, that is x. This I can rewrite as y minus 2x. Here I have 1 over d square, that is I have to integrate this with respect to x 2 times. Now integral of y minus 2x with respect to x is, y is considered as constant. So y into integral of 1 with respect to x is x, minus 2 times integral of x is x square by 2. So I will have yx minus x square. Again I have to integrate this with respect to x, that is y as it is x square by 2 minus x cube by 3. So that I have written here, and this is my particular integral. And finally we write general solution by adding complementary function and particular integral. Do not forget to write down the general solution, otherwise you can lose 1 or 1/2 marks for that. So in this session we have discussed 2 problems on the shortcut method of finding particular integral when right hand side is a polynomial function, and we understand the difference between these 2 problems, that here we are not able to write this function as power of linear factor. So I have taken d square common and I have written in this form. If you wish you can take 2d dash square common also, and in that case you have to write this as d square by 2d dash square plus 3d by 2d dash plus 1. So now this is going to be your x in that formula, 1 over 1 plus x, and there are chances that you will get different solution. Whatever solution you will obtain, that might be different from this particular integral, because this particular integral is obtained by taking d square common. So here you can see this is our x in the binomial series, and here you can see this is our x which is different from this. Here I have d dash square, here I have d square, here I have 3d dash, and here I have 3d. So whatever particular integral we will obtain, that is going to be different from this particular integral, but both will be considered as correct answer. Either you are considering d square common or 2d dash square common. So that is main thing here. And in previous problem, it was possible to write down fd d dash as a square of d minus 3d dash. So here things become easy, and here also we have taken d square common. If you wish, you can take 3d dash common and write this as d over 3d dash minus 1, and try to apply binomial theorem. So in that case also there are chances that you will get different particular solution. So both the particular solutions are considered as correct. So this is another shortcut method for finding solution of non-homogeneous equation when right hand side is a polynomial function. We have discussed 3 shortcut methods, and those methods depend on the particular function on the right hand side. First one was exponential function, second one was sine or cosine, but in this form, sine of ax plus by or cosine of ax plus by. Third one is each term of fxy is in this form, or we can simply say that polynomial function in x and y, and in each of the 3 cases we have different methods for finding particular solution. So you must be aware about those 3 different methods, and for functions other than this we are not able to apply shortcut methods. So in that case we have to go for another method that we are going to discuss from next lecture. So this is all about this session. I hope you like it. Thanks for watching.